Complex numbers are the completion of the real numbers. The way this idea comes about is from the fact that, again, the root of a polynomial is always a complex number. So we can always decompose our polynomials into different linear terms whose zeros are complex numbers. Now, another fact about complex numbers is, in a sense, they're two-dimensional, in that on the complex plane we have a real axis and an imaginary axis. So each number in the complex plane is given by two pieces of information, or in other words, an ordered pair. And we represent this number as a plus bi. Now let's go ahead and graph a few different points in the complex plane. So again, we're going to graph these points, and you can either think about them as complex numbers or ordered pairs. Again, this is our real axis, this is our imaginary axis. Let's go ahead and start with this point here. So we're going to move 3 units over on the real axis and 1 unit up on the imaginary axis, and this will be our point. Now for the second point, we'll be moving 1 unit over on the real axis, then a negative square root of 3 divided by 3 units down, and this is our second point. Then finally, for our third point, we'll be moving 7 units in the real direction, then negative 3 units down, and this is our point 7 minus 3i. Let me go ahead and just point out that generally we call the real part of our complex number the real component, and we call the imaginary piece of our complex number the imaginary component. So now that we can graph different points on the complex plane, let's go ahead and sketch a few different sets. And in this problem, we're going to go ahead and sketch the following two sets. So in the first set, we're trying to sketch all the complex numbers whose real part and imaginary part are larger than 1. And then in the second set, we're going to see that the sum of our real and imaginary part has to be less than 2. Starting on part A, again, we're going to sketch our graph. So we have our real axis and our imaginary axis. And we want our a values to be larger than 1. So if we think of, again, complex numbers, a plus bi, as ordered pairs, then this is saying that we want all the x component of our ordered pair to be larger than 1. Therefore, if we look at the line x is equal to 1, then everything to the right of that will satisfy this condition. And with a similar sort of logic, when we have our b values larger than 1, this is telling us that the y component of our ordered pair has to be larger than 1. So therefore, if we look at the line y is equal to 1, then everything above this line will meet this condition. And the set of points that meet both of these conditions are going to be where the green shade and the blue shade intersect. So namely, this piece here. So let me go ahead and draw a clearer picture. The set that we're going to be looking for is the following. Now let's push over to part B. Here, this time we have that for a given imaginary number, a plus bi, we want the sum of the real part and the imaginary part to be less than 2. Again, the simplest way to think about this is thinking about an ordered pair. So we have the ordered pair a and b, and we want a plus b to be less than 2. So let's go ahead and just think about what a plus b is equal to 2 has to look like. Again, a is our x component, b is our y component, So let's think of A as our x, we'll think of B as our y, and now solve for y, and we see y is going to be equal to a negative x plus 2. So let's go ahead and graph this line. This line will look something like this. And so what this line represents is that a point on this line has an x component and a y component, where if we add them together, we'll get that this is equal to 2. So therefore, we want all points where we add the real part and imaginary part to be less than 2. So in other words, we want all the points below this line and not including this line. And you can check this real fast by, let's plug in a point below the line, and let's plug in 0, 0. So 0 plus 0 is less than 2, and therefore all the points in the set are going to be below this line here, but not including the red line. So I'm going to make this red line like so. And this is going to be a sketch of our graph, or a sketch of our set. Now, like real numbers, we have this idea of absolute value for complex numbers. And remember that the absolute value of a real number represented how far the real number was from the point 0. And the generalization of this for complex numbers is called the modulus. So embedded inside, again, our complex plane, we have this real axis here. And let's say this was the point 2, 0. Then thinking about this point as a real number, the absolute value of 2 is just equal to 2. Now again, the modulus is going to be the same idea. We have this complex number over here, a plus bi, and the modulus is going to be how far this real number is from the origin. And since a point determines, again, a right triangle, who has base A and height B, then the modulus is going to be the hypotenuse of this triangle. So let's go ahead and look at the definition. So the modulus of a complex number is defined to be the following. With the idea of the modulus in hand, let's go ahead and look at one more example, and this is going to be example number 4. Again, we're going to sketch the following set. This is going to be given by the set C, which is all complex numbers, where we have that the modulus of our complex number is between 2 and 5. So remember that the modulus is how far a complex number is from the origin, and the circle is defined to be all points of constant distance from the origin. So therefore, the modulus of z is equal to 2 is a circle of radius 2, and the modulus of 5 is a circle of radius 5. So therefore, we want all the points that are inside our circle of radius 5, and we also want all the points that lie on our circle of radius 2, and everything in between. So here is our set.